infinities. So he now uses the solution from the one-dimensional case and rewriting it to get a formula which then is much more efficient. So here you have a very good analytical solution to this 2D problem. If ever you want to need it, if you want to have a nice test case, then you have the analytical solution here. Then you have actually all the source code printed out here in Fortran 77. So if any of you guys programming Fortran, this should be easy reading. For the rest, it will be weak, I guess. I don't have the codes anymore on files, sadly. So if you want to test this program, you have to punch in all this yourself, which can be rather boring, I would say. And I believe also we have the Pascal here as well. Yeah. So here we have the Pascal language. Any of you touched Pascal? Any you have? Okay. Not bad. So it was actually a cute language, but it's sort of the basis before it started with C and C++. Yeah, I want to go through this. We have another example which I rather will look into instead of this. It's just here defining these matrices that does this restriction and prolongation, the integrity transfers. So you can have a look at it if you like. Yeah, the full approximation storage. If you can recall from the beginning, we started finding this residual equation. But to obtain the residual equation, we had one demand. Your equation system must be a linear equation system. If it's nonlinear, you can't use the residual equation. The reason for using the residual equation was that on the coarse level systems, you get the right-hand side from the final level above. And then you have to guess some initial field here before you start solving this equation. And then an error is so nice to guess, because we know the error is going to be small. At least it will be after you have done some equations. So you choose 0, a very good initial guess. So that's sort of the argument for using the residual equation. But now, say you have a nonlinear equation system, you can't use it. Then you are stuck. Then on every grid level, it has to be the real physics. You can't use the residual equation. So it's just described here how this one can be done. So I won't go through this. You can look at it if you're interested. Not that many problems will be nonlinear anyway, so it's not so interesting actually, although you can find these routines as well, yes. Yeah, and that should be the end of the multigrid. Now looking into the compendium we had here, and then part 2. So this was some work I did implementing multigrid into the Sol algorithm for the Poisson equation only. So here you will then find a little bit more say hands-on, but the multigrid I used was fairly straightforward, just recycles directly. So here, first start with the traditional algebraic equation system, and then they're using the same notation, everything, finding the residual equation, defining here a V-cycle, the integrate transfers, so everything should be well known to you now. So here you start on the fine mesh, and here you have your V-cycle. Iterate here, finding the residual, transfer the residual down here to the new right-hand side on the course level. Iterate here, and then transfer the residual, and so on, all the way down to the course's mesh, where you have to solve the equation system. Somewhere you have to solve it. Of course you do that on the course's mesh. And then nest your way up again, adjusting every solution on every level. So here, just a little numbers for the amount of storage you need. You need 2 whole fields on every level. But in 2 dimensions, you see it's hardly anything additional, 4/3. And in 3D, 8/7, this is very close to 1 indeed, so it's very, very cheap when it comes to memory requirements. Yeah. The transfers, that's a little bit messy here with the Solar mesh system. If you remember Solar, we used the MAC system, marker and cell. So for one computational cell, you have the pressure in the center. The velocity is located on the cell faces. But the equation we are solving, this is a Poisson equation for the pressure. So our unknowns are located in the cell centers. So this will be quite different than in the material you have been given by Orsett, the handwritten material. He had stored everything in the corners. But here, with the centers, well, not too hard, but I mean, you have to choose how should this big cell here talk to these 4 cells. So the averaging interpolation systems there have to be somewhat different. Of course, fairly easy, going from the fine mesh to the coarse, you just add these 4 and take an average of them. And going the other way, when you have a coarse adjustment here, he will then influence all these 4 fine mesh solutions. Fairly straightforward. Yeah. So then it's a question on the coarsest mesh, how to solve it. If you are lucky, then you have on the coarsest mesh just 1 single cell, 1 unknown. Of course that one you solve directly. But depending on the geometry, the number of cells in X and Y direction, you risk to have more than 1 cell on the coarsest mesh. Also, sometimes you want to stop, you don't want to telescope all the way down to the coarsest possible mesh. Say you have only 3 or 4 or 5 mesh levels, then solve it. And I think here I just used a whole bunch of SOR iterations just to be dead certain that I had a good solution on the coarsest mesh. This mesh will be so coarse anyway, so it's very cheap to find a good solution either way. But it has to be solved, that's important. Now we are talking smoothers. So far you have been taught about the classical, Jacobi and Gauss-Seidel as point iterations. So you sort of discretize your equation system, and you'll have in 2D then typically a 5-point discretization star when we talk about double derivative in each direction. Here you have some different ways of thinking. The red-black Gauss-Seidel pattern. Not too happy with red-black. I think of this typically as a checkerboard pattern, so I would call it white-black, but okay. Never seen a red and black chessboard. So the idea then goes as follows. The Gauss-Seidel, remember, then you should always use the freshly updated values whenever possible. You don't overwrite you overwrite your unknowns inside a matrix directly. But now when you sweep over the entire domain, you just you do it in two stages. First stage, you take, say, all the red cells, every other cells. So that means the updating is going to be based on pure old values, or values from the previous iteration. Then you have to do it once more to take the black ones. Then you will have four neighbors, which would be just from the first stage. That will just be updated values. So it's still Gauss-Seidel, but it's a mix. So the first half, that would be Jacobi, and the second half, yeah, that's pure Gauss-Seidel. Just based everything on the updated values. Then you have a line solver. Now, what's a line solver? Well, when you are in 2D or in 3D for that matter, you think of all your unknowns along one single line. They are just your unknowns. The rest we treat as known. Of course they are not known, they are also unknowns, but it's very cheap to solve one line of unknowns directly, using a direct method. Because that will be a three-diagonal matrix, you can solve it very easy with the Thomas algorithm. So it doesn't cost much, and it's quite efficient to find a bunch of unknowns along a line. Will be of order n operations, so it doesn't cost much. And then you have to take the next line and the next line and the next line to sweep over the entire domain. Of course you have. That will be then one iteration. So instead of a point iteration with like a Gauss-Seidel, you will have a line iteration. And the zebra, sort of the same philosophy as red-black. Take the even line first and then the odd lines afterwards, instead of taking them in a sequence directly. Then you have something called an ADI, alternating directions implicit. But then you switch. You take one line in the x direction and then another line in the y direction, and then you alternate all the time until you have covered all lines in the x direction and all possible lines in the y direction. And if you are in 3D, all lines in the z direction. So this one has a point, which we will come to later. For now, to play around with multigrid with different scenarios, I have tried here to play around with different number of cells in the x and y direction, and different sizes, delta x different from delta y, and see the effects. So that's sort of the task here. So here I used the residual, but I sort of have designed a test problem with an analytical solution, so I know the actual adder as well. So here also you'll see the effect of wasting time finding the solution all the way down to machine accuracy, because here you have the real adder to compare with anyway. You'll see. So the first case, here playing around with the different solvers. Here I've just used a rectangular area, one iteration on the way down and one on the way up again. So I have 7 number of levels with 64, and that's sort of the maximum. So the coarsest mesh will be one single cell. And in my model problem, very easy model problem, double derivative equal to 0. So it's actually a Laplace. So whatever you start with is going to be an adder. So I just use random numbers here. And here then you have the performance, sort of a log-log plot. Well, actually it's just a semi-log plot. Here you have the number of work units. Remember, work units, 1 unit was 1 iteration on the finest mesh. And on the y-axis you will have the log of the 2 norm of your entire equation system. So the classical methods, the Gauss-Seidel, he starts very easily, very nicely, reducing the error, and then he sort of levels off and getting very inefficient. This we have seen before, very fast in removing high frequent noise, but low frequent noise is going to take forever to get this alloy down to some machine accuracy. Here you can think of this as roughly the number of digits in your solution. And double precision you have 16 digits. So you can't get beyond or below minus 16 here. The line solvers, Zebra, ADI, not so efficient either. An SOR with a fairly decent omega, he is actually more efficient. Not in the beginning, but he will beat them in the end. So he's not so bad. But now look at the different multigrids. Depending on the choice of smoother, you see the effect, which one is smart here. So you have this Zebra patterns with line and ADI. That's the best one. A pure line, very efficient indeed. The alternating direction simplicity without the Zebra pattern, very efficient. And the best one, just pure Gauss point iteration actually, very efficient indeed. So with 60 work units, you are down to machine accuracy. And here you have the real anode, since you know the analytical solution. And then you can see the point. You can't get it more accurate than, say, 4 or 5 digits. So here you can sort of test what you asked for. How far should we go here? When should we stop? Well, you should stop when you have reached this anode level here. So doing more than 20 iterations is a waste, 20 work units here with this Gauss is a waste of time. To find machine accuracy, you have to use 60, but you should stop after 20. Because here you are talking about the real anode. So why push all the way down to machine accuracy? Waste of CPU. Second case, I just changed the length of my domain. So in X direction it's now 10 times the Y direction. But still the same number of cells in each direction. So still seven different meshes. And here all of a sudden this Gauss point iteration that was the most efficient in the first case is now quite inefficient, quite terrible. And the line solver in the X direction alone, he will explode. You can't even get a solution. The fastest one, that's the line in the Y direction. This has something to do with the geometry. He is quite efficient in, say, propagating the information in one direction versus another direction, these line solvers. So the correct line choice will be very efficient. The wrong choice is a very bad idea. if you really don't know the direction you should choose, you're not certain, I mean, which way does it flow here or whatever, then the ADI is the safe choice. And this also then is the reason why a lot of people use this. So it's sort of a balance, maybe not the most efficient, but at least decent, regardless of the geometry for your case. And here again, the actual adder. So again, stop after 20 work units, not go all the way to machine accuracy. So here, same as the first case, you had 7 possible grid levels. So now I used the ADI smoother, and just to play around to see the efficiency depending on the number of meshes you use. So here the efficiency just on the fine mesh, just one coarse mesh, 2, 3, and so on. And here 4 to 7, really no change. So I mean the idea is that when you are on a sub-mesh level, how to find a solution there? Well, you can solve it when you are there directly, or you can still use multi-grid on an even coarser mesh. What's most efficient? So you see from 4 to 7, it really doesn't matter. Of course, when you have multi-grid operating, then this one is fairly easy. You just continue as long as possible. But you could just as well have solved it on the sub-level 4. That will be just as efficient. That's interesting. I can see that one. Here, I'm just playing around with different combinations of the number of iterations on the way down and the number of iterations on the way up again. And the most efficient one, that's the open squares, which is 1 on the way down and 2 on the way up again, for this example. So even this 5, 5, it's actually not efficient at all. So don't overdo it. These new 1 and new 2, they are normally quite small, as you can see from the figure. Finally, playing around with different number of cells. Here it's a little tricky then to compare the different simulations, because you have a different number of internal cells. So if you talk about work units, the work unit definition is going to change from the different simulations. So to be able to compare them, then I had to sort of define my work unit on the finest mesh, and then sort of adjust these accordingly, just to be able to put this in the same graph. So this one I'm quite proud of. So here you have the total number of unknowns versus the work unit, the adjusted work units, so they can be plotted in the same graph here. And yes, it is indeed very close to a straight line for the different cases, meaning you solve n equations with order n operation, the fastest method possible. The next one, the fast Poisson solver using a fast Fourier transform, will be n log n. So he will always curve a little bit upwards. Multigrid is the best. But remember, this problem then is very neat, close to square, rectangular cells, Poisson equation, very easy to solve. So it can be more tricky than this, but it's possible. as you can see, to show this. Yeah. The rest here, maybe not so interesting. I can just show it to you. Some test cases. The square cavity. Venus number 1000. And the method, yes, it worked actually quite nicely. It had some little noise in the beginning, but it was operating fairly decent. And here I now check with a physical criteria. I use the maximum of the divergence of the entire field. So that's the nice thing with the projection method in Sola. You can do some physics with the anode, not just using a residual or something. Also here I played around using the switch, if you can remember this one, the beta. That was in the split step method. When you calculate the tentative velocity field, you normally will use the old pressure, the pressure from the previous time step. But beta equals 0, then you skip the pressure altogether. I mean, this tentative velocity field is going to be wrong anyway. So you have to solve a Poisson equation afterwards. So, but here you can hardly see that you have any difference. A little bit noise here after 3 recycles, but for the first 2 you hardly see any differences at all. So it really doesn't matter with multigrid. With other methods, I won't really, then I don't really know. Then you have to try yourself. Yeah, I won't go through this. Here, it's a test of the periodic boundary conditions. This is a sort of a nice little test case. So keep this in mind if you're ever going to use cyclic periodic boundary conditions. So I start out with an open area, and I have periodic boundary conditions in the x direction. So whatever goes out here should come in here. And then I start, initially everything equal to 0. And then I create just a noise. I just set up one velocity here, one u and one v. And then I do a couple of iterations, finding a solution here, or just some time steps. Of course, this initial noise is just going to die out. So you must stop before everything is back to 0 again due to viscosity. So just find a solution at a certain time level. So here you have the streamlines, and here isobars from these disturbances. And then you create the exact same disturbances, but you move the position in the x direction. So here I moved it to this one. And now these two images should be identical if you have the correct boundary conditions. And if you had made a copy of one of them and put it on top of the other by just moving it, you will see, yes, they are perfectly the same. So it's a very easy test case for periodic boundary conditions. Finally, I wanted to test in a real case, so I started with the startup of the Poisson velocity profile. And there you have an analytical solution. I think I've shown it to you already by Szymanski. It's an old classic solution, it's easily to be found in any textbook. My worries here was that this flow is fairly easy to find. I mean, on t equals 0, you switched on a pressure gradient, and then the velocity develops into a steady state. And all codes will be able to find the steady state, of course. Here I was more interested in, can you find the correct time development? But for this problem, the time development is not that challenging. It's fairly easy. So I did it more nasty with an oscillating pressure gradient. So this is something else. So here you sort of switch back and forth. The pressure gradient goes like cosine omega t or something. And then you can have a lot of different funny velocity profiles, never sort of reaching towards a steady state. Because my worries then was that the time development that was solved using just a first order Euler step. And doing thousands of time steps won't just a first order method accumulate a lot of errors so that in the end you get you lose track of the correct time development. So then I thought this should be a much tougher test case. But actually it fits rather perfectly. So if you really want to test the code here for time development, I can recommend this test case. And I believe you have been given here the solution. Yes, should be here somewhere. Transient channel flow. So you have the analytical solutions here somewhere. Yeah. So there you have one, and the oscillating is a little bit more messy. Here. Yeah. So you get quite strange velocity profiles, depending on. I mean, you have two effects here. You have the size, the strength of the driving force, the pressure gradient, and then versus the frequency. I mean, if the frequency is too high, nothing is going to happen. The fluid just vibrates. If the frequency is too low, okay, then you have just a classical Poisson profile, developing first one side and then easily go back to the other side. So there are some parameters you can play around with here. Okay, that was the material you have been given for multigrid. Any questions? Yeah, one final thing about multigrid. When I did this programming, implementing multigrid in the Sola algorithm, and you have a geometry, here is your domain, say maybe this is the square cavity test case, and then you divide it up in a number of cells. So this then should be the coarsest mesh, well maybe the second coarsest mesh. But then, if you want to program this on all mesh levels, you have to take the boundary conditions into account. So then you will have the ghost cells looking something like this. And then use the boundary conditions using these ghost cells. Or, if you want to do it more correct, you don't use these ghost cells, but you have to program your boundary cells accordingly. So if you have a Neumann condition here, saying that the pressure outside should be equal to one inside, then you have a sort of a special version of your discrete equation system for these points. And this is also a corner point, so you also have to do it here. But here you have the ordinary derivatives and double derivative expressions. So on a fine mesh level, I will draw all the lines here. You have to do then again boundary cells like this, and again corner point. We will have a special version since you then use these two ghost values using for the boundary conditions. But that means on every grid level you have to program also the boundary conditions. And this is fairly okay to do in a square rectangular domain. Still, I used a lot of time or wasted a lot of time doing it, so I won't recommend it. But say if you have a more complex geometry, maybe you want to simulate something like this, for instance, a flow here with a backward facing step and an obstacle. Okay, be my guest. How the heck should you do this? Well, you need a mesh system, of course, but the coarsest mesh here, I mean, you have to follow the structure here somehow, and somehow like this, and somehow like this. So that should be the coarsest mesh you have the possibility to do here. And if the geometry is even worse, of course, this is not really possible to take advantage of the geometry directly. So here, I'll call this a geometrical multigrid. Yes, you can easily use on every level the correct geometry. Here, and with verse geometry, you really can't do it. So what do? You use an algebraic multigrid. Meaning, you take on the fine mesh system, you create your equation system, and then you let the mathematicians worry about the rest. So then everything is programmed for you. He doesn't take into account sort of the geometries on the coarse mesh systems because it's not really possible anymore. Everything is just solved mathematically. I won't go through the theory there, very tedious. But in practice, this means that when you're firing up Fluent, CFX, Star CCM, any of those, and you choose multigrid, this is the option you get. They don't use it like this. It's not possible in the general case. In general, then, this algebraic multigrid won't be as efficient as a geometrical, where you can take advantage of the geometry, like in my test cases. But in a real case, no. Of course, it will be something like this. And these routines you can find on the internet if you search for them. Freely available, no problem. In most languages, Fortran, C, whatever you are interested in. So that will be sort of the basis. It will still have the same questions for you if you switch it on. You will ask, should we use V cycles, W cycles? How many iterations on the way down? How many iterations on the way up again? What kind of smoother do you prefer? So you'll have all these questions as well. So that's actually also the motivation in this course to push you through this theory, or at least some insight into what multigrid is all about. Just be aware, you are going to use these in the future. Okay? Then for tomorrow, we'll be back here. We will then have a peek into conjugate gradient methods, which is a decent alternative to the multigrid. In theory, they're not so efficient, requires a little bit more memory, but the source code will be this big. Very easy to program, very efficient. So conjugate gradient, that's the topic then for tomorrow. The material is already out there. It's one recommend. The Krylov 1 and 2, they're just handwritten notes, but they are mostly then based on this one. It's written by a student, I think, who called it conjugate gradient made painless. So it's easy. So we will go through this and have some demonstrations also tomorrow. Any questions from you? Then we stop here.